So today we're going to be learning the properties of the transition metals. We're going to be adding to our periodic table in that you've shaded in this group. A thing that we're not going to be adding is we are actually not going to add a charge written above this group, and we'll talk about why shortly. Yes, Yossi?
Should we put this under metals or non-metals?
These are metals. The transition metals is this group. We list them under the metals. We're going to talk about some of the metal properties in a little bit more detail. But most of these properties are things we've actually already discussed. So a lot of what we're going to be talking about today is going to be stuff that's just like indulging your curiosity, because the thing about this group, the thing about the transition metals is they're pretty firmly outside the realm of like middle school level chemistry. I'm hearing a lot of side conversations. I'd love it if we could get that into wraps. A lot of the chemistry we've done has been focused on what we call the A groups of the periodic table. Those two wings, right? The 2 columns on the left and the 6 columns on the right. Today we're in this middle section. All of those columns are labeled the B group. So we go basically from 3B to 12B are the groups that we call the transition metals. And these groups don't really work with the octet rule. We're going to talk about why. But before we talk about why, I do want to make something really clear. The next bit of this lesson, where I talk about why these things don't behave like the A groups, is really not middle school level chemistry, right? It's closer to like AP Chem, the kind of chemistry class you might take in a high school if you wanted to get college credit. So this next bit, I'm gonna like show you some pictures and things that are gonna make you go like, I don't like the look of that. No thank you. And your brain's gonna like ring a couple alarm bells. And I just want to be really clear, that is an okay response to have, because the portion of today's lesson that is like, hey, I'm just gonna give you some hints about like what is coming up in high school. I am not going to hold you accountable for the high school level chemistry on any tests or on any class kicks, okay? Right? You're not going to be held accountable for anything high school level on tests or class kicks. This is included because I always have a number of students who are like, but why? You must tell me why. Why are the transition metals not like the A groups? And so we are going to answer that. In the past, we've started each of these lessons off by being like, okay, draw me some planetary models and give me a charge. I'm never going to make you draw a planetary model of any of the transition metals. It's unlikely that even a high school teacher would ask you to draw a planetary model for one of these transition metals. And the reason why is that once we get to the transition metals, the atoms are now sufficiently complicated that the planetary model is not a really good approach to use here anymore. We cannot just write a single charge above these groups. We can't just do a planetary model of them. What's going on with the electrons in the transition metals is way more complicated. They have a whole different sort of set of models that you need to understand if you want to learn why they do the things they do. But what it boils down to is there's like a whole bunch of different places that electrons can go into. And it turns out that with the transition metals, there's oftentimes more than one path to stability when it comes to forming an ion. So with things like sodium or the alkali metals, we can look at those planetary models. We could say, oh, all of these have one valence electron. They're always going to lose one valence electron, so they'll always form ions with a charge of +1. With the alkaline earth metals, we could say, oh, they're always going to form ions with a charge of +2. With the halogens, we could say, oh, they've got 7 valence electrons. They always want one more valence electron, so they'll always be -1. With these transition metals, because the places where we put their electrons are so much more complicated, there's more than one way that they could end up losing electrons in order to become stable. So for example, iron has two different paths to stability. One path to stability involves losing 2 electrons and forming ions with a charge of +2. But there's a whole separate way that iron can become stable that involves losing 3 electrons, and that means iron can form cations with a charge of +3 or +2. So, and this is true for most of the transition metals. They have more than one path to stability, so there's more than one type of ion they can form. So let's talk about how we draw these out and how we talk about them. Let's use iron as an example. Iron has a symbol of Fe, and there's 2 different ions that iron can make. It can either make iron with a charge of +2, or it can make iron with a charge of +3. If I wanted to write it out in a chemical formula, this is how I would write it out, either iron +2 or iron +3. The names of these cations include information about their charges. So if I want to talk about say an ionic compound that uses iron with a charge of +2, the way I would write out that name is I would say, hey, this is an iron 2 cation. But the 2 is written using Roman numerals in parentheses. So if you ever see Roman numerals in parentheses, that is saying, hey, this is the charge of this particular cation. We can't just say, oh, it's an iron cation anymore, because there's more than one type of iron cation. So for this one, iron with a charge of +3, we call that iron 3, with the 3 as Roman numerals in parentheses. So weird thing that comes about as a result of this, we could have multiple ionic compounds made out of ions from the same element. For example, I can't just say iron oxide, because there's more than one type of iron oxide. I have to specify, am I talking about iron 2 oxide or iron 3 oxide? Right? So I could have iron 2 oxide, which would use iron with a charge of +2 and oxides with a charge of -2, or I could have iron 3 oxides. And these 2 chemicals have different chemical formulas, even though they are made of the same elements. So you'll see, am I still in frame? If I'm here? Okay. Iron with a charge of +2, if that's bonded with oxide, we can be like, okay, well that's pretty simple. We've got iron, it's a charge of +2, which I can tell because the name is iron 2. And then we've got oxides, which are -2. So this is my chemical formula. Make sense so far? But for iron 3 oxide, which I would write out the name like this, iron 3 is my cation, so it's always name of the cation, name of the anion. For that, the iron has a charge of +3, while the oxygen is only -2. So this isn't a real compound yet, because I've got 3 positives and only 2 negatives. Lisa, can you help me figure out how many of each atom I need?
2 irons and 3 oxygen.
Yeah, I need 2 irons and I need 3 oxide anions, because then I have a total of 6 positive charges from the irons, right? 3 from the first, another 3 from the second, and a total of 6 negative charges from my 3 oxygens. -2, -4, -6, so in total this is neutral. So here I have 2 different chemicals. These are separate chemicals. They would behave differently. This one is iron 2 oxide, and this one is iron 3 oxide. The names for them are name of the cation, so iron 2 oxide, or name of, this one would be iron 3 oxide. So we read it out by reading out the Roman numerals as though they were numbers, but we write it down with the numbers in Roman numerals. The thing that is confusing about this is oftentimes people hear numbers and they assume that those numbers refer to how many atoms there are, but that's not true. Iron 2 oxide only has 1 iron 2. Iron 3 oxide has 2 iron 3s. Remember that in ionic compounds, the name doesn't tell you anything about the subscripts. To figure out what the subscripts are, you have to think, okay, what are the charges, and then how do we make it so we have a balanced, neutral chemical compound? So things I might expect from you, because when we talk about the transition metals, we are starting to move outside the realm of like really middle school level chemistry. I would expect you, if I tell you that we're dealing with iron 2, to be able to do something, to be like, oh, well, here's the compound with iron 2 and oxide. Or if I tell you, hey, we're dealing with iron 3, iron with a charge of +3, then I'd expect you to be able to say, okay, well, here's the chemical formula for iron 3 oxide. What I do not expect you to be able to do is to know inherently that iron can have a charge of +2 or a +3. I don't expect you to know the charges of any of the things in the transition metals. If I'm asking you to work with the transition metals, I will always tell you what their charges are. Okay? So for the things in the A groups, if I tell you you have something that has sodium and oxygen, I expect you to be able to tell me the charge of sodium, because that's in column 1A, it's an A group. I expect you to be able to tell me the charge of things in the A groups, but I will not expect that of the things in the B groups. For the B groups, I will always tell you the charges. Okay? So that's like where we fall on this part is in the, like how much of this I'm actually gonna hold you responsible for. All right, so let's talk about why the heck this happens, because people always wanna know why. And this is the part where I wanna be really clear. This is not middle school level chemistry. You are not going to be expected to fully comprehend this. This is just an answer to the question, but why though? Because I always have students who want to know, who want that little bit of extra depth. So if you look at this next image and it makes your brain go, I don't like that, that is an okay and normal response, right? Everyone okay with the fact that they're about to see an image that's really unpleasant? All right.
I don't like that.
Yeah, how many people are like, uh-oh, I don't like that. All right. So, we have been dealing with the octet rule. The octet rule works for the A groups. Here is what actually causes the octet rule. So before I've been telling this oversimplification of, every row of the periodic table is an electron shell, and the electron shells can hold 8 electrons except for that first one, which can only hold 2. Really what's happening is that there are different types of places where electrons can sit. The first type of place that electrons can sit, we call s orbitals. The shape of them is a sphere. And what this sphere represents is probabilistically, the electrons are most likely to be somewhere in here. That's what that sphere means. The electrons are there's probably 2 electrons somewhere in a shape like this. And that can hold 2 electrons. I want to point something out. You know how we keep having hydrogen and helium being a little bit weird and wonky because that first shell only fills with 2 valence electrons? What's really happening there is the first shell is just a single s orbital that is capable of holding 2 electrons. Okay? Everything in those first 2 columns, all of our alkali metals, hydrogen, all of our alkaline earth metals, and also technically helium, these things have their valence electrons in an s orbital. So s orbitals like to become stable by emptying out, right? Which is why these things tend to lose an electron to form ions with a charge of +1, or lose 2 electrons to form ions with a charge of +2. Then we have p orbitals. P orbitals, technically they look like this. There's 3 of them, and they look like this. And each of these 3 things can hold a pair of electrons. And these areas are just places where the electrons are more likely to be. But really the important thing to know about them is there's 3, each one can hold 2. P orbitals can hold up to 6 electrons. That's the thing that's actually important. Hey, what's 6 plus 2?
8.
8! like the octet rule. These 6 columns over here, the rest of the A groups, they keep their valence electrons in p orbitals. So the octet rule is a thing that works for all of the elements that keep their valence electrons either in s orbitals or p orbitals. P orbitals can hold 6 electrons. You will notice there's 1, 2, 3, 4, 5, 6 electrons over here in this segment of the periodic table. Then we've got this next kind of orbital. They're called d orbitals. These are just like pictures of where the electrons are likely to be. The shape of the pictures is not actually what's important. What's important there is that there's 5 of them, each of which can hold 2 electrons. So d orbitals can hold 10 electrons. Hey, how many columns do we have in these transition metals? 10. The transition metals are the set of elements that keep their valence electrons in d orbitals. This area of the periodic table is also referred to as the d block. This section is sometimes referred to as the s block. This section is sometimes referred to as the p block, right? It just means we keep our valence electrons in that particular type of orbital. All right, so that's the d orbitals. The important thing about the d orbitals, there's 5 of them. They can hold 2 electrons each, so 10 electrons can fit in d orbitals. That's why this section of the periodic table is 10 elements wide. We're starting now to get into this area of like, hey, why is the periodic table shaped like it is? And then lastly, we have these ones. These are all the f orbitals. There are 7 of them, so how many electrons can fit into the f orbitals? 14, because we've got 7 f orbitals, each of which holds 2 electrons, so we've got 14 elements. And that's, hey, that's the lanthanides and the actinides. This bottom segment of the periodic table that we pulled out, they keep their valence electrons in the lanthanides, in the f orbitals. Yes?
Should we color those in?
Not yet.
Okay.
We'll cover the lanthanides and the actinides later. So this is what is actually going on. When we talk about the octet rule, the reason why it only applies to these 2 columns and these 6 columns is because that's where we end up with a number of valence electrons that adds up to 8, 2 plus 6. 2 from the s orbitals, 6 from the p orbitals. That's where the octet rule actually comes from. In high school, you'll be forced to engage with this. In high school, they'll make you do things like say, hey, for a given element, what orbitals are all the electrons in? You'll have to be like, well, first they go into the s orbitals, and then they go into another s orbital, and then into a p orbital, and then and you'll have to do this whole long thing that's a bit of a pain in the butt. But in middle school, you don't need to do that. Yes, Emily?
Can I take a picture of that?
You may, and also, I just want to be really clear, you are not at all responsible for this information on any kind of testing. And the most important thing about this is just to know, like, s orbitals can hold 2 electrons, right? P orbitals, 6 electrons, d orbitals, 10, f, 14. That is honestly the important part.
Actually, I think my mom showed me something like that when I was in like 4th grade.
It's possible. But the thing about this that's valuable to me is it helps me understand the shape of the periodic table to be like, oh, 2 columns here, 6 columns here, 10 columns here, 14 columns there. That's the part about this that helps me, is to understand the periodic table. All right. So, back to the middle school level work. Transition metals are metals. They've got all the metal properties. They're malleable, they're ductile, they're conductive. They tend to form cations, which are, say it with me, positive. Right? They're going to have high melting points and so on. Additionally, it's worth noting, transition metals are kind of the most metally of all the metals. Whoa. This is where we find the things that are most malleable. Elements like gold, absurdly malleable. Right? This is where we have things that are extremely conductive. Right? Copper, incredibly conductive. Gold, incredibly conductive. This is where we have things that have, really high melting points, like iridium, which is an absurdly high melting point, right? We use iridium as like a crucible that if we want to melt other metals in it without worrying about the iridium melting. This is where we find things that tend to have these properties of metals most extremely. Are there exceptions? Yeah, there's always a couple exceptions. Mercury's a little weird, But broadly speaking, this is where we have like the most metal of the metals. But when you think about metals, most of the metals that you think of when you're like, hey, what do I think of when I think about metals? They're in the transition phase, right? These are the ones that you really think about. Now, we have talked about metallic bonds already, but just to review, remember that one of the things that is special about metals is that they're capable of this type of bond where it's just like, hey, full electron communism. The valence electrons don't belong to anybody, they belong to everybody, and because of that, we are all able to achieve stability in our own lives. It's almost like through sharing and equitably distributing resources amongst communities, we can achieve collective stability. And maybe there's a lesson in that to be learned. So here's just a picture to remind you about these metallic bonds. It is the metallic bonds that are the thing that make these metals so conductive, because they'll just pass electrons from one atom to the next, to the next, to the next, to the next. So if you put in extra electrons at one segment of the periodic table, those electrons just get passed along. That's part of what makes metals special. Because of this, in chemical formulas and chemical equations, you'll see metals just sitting out there by themselves, right? Because they don't have to be in a chemical in order to be stable, because of the metallic bonds. All right, that is it for today. You can move on to the class kit, which is, I believe, Chem14 transition metals.